Stanford University.
So I'm going to talk today about power systems engineering, utility planning, and operations. And I know a lot of you are thinking that sounds really boring and really tedious, very dry. And actually, you're right, it is. But the implications of this are really important. The implications of this are how we can accommodate more renewable energy onto the power system at a reasonable cost without breaking the bank, while keeping the lights on and maintaining reliability. So with this, I'd like to just sort of get a feel for how many folks here would like to get more of their energy from wind and solar and other renewable energy sources? Well, that's great. And how many of you think that because the wind and the solar, they're fluctuating over time, you can't perfectly predict when it's going to be sunny or windy, that we're going to need a lot of storage to help back this up to provide us with firm power? Okay, so I'd like to introduce you guys to Renewatopia. In this land, Renewatopia, we've got these people get all of their energy from renewable sources, like this wind farm here. Wind, unfortunately, doesn't produce much during the middle of the day in Renewatopia. So in order to deal with that, they've got a storage system at their wind farm, and that helps to level out their output. So they've got nice, flat output. Renewatopia also has a big solar farm. And the solar farm output looks like this. Unfortunately, Renewatopia likes to watch TV at night, and the solar isn't producing much at night, so they've got a big storage system on that to help level out that output. And so things are happy in Renewatopia. They're contributing to helping to deal with the climate change issue. They're getting all of their electricity from renewable sources, so things are all good, right? Well, it turns out in Renewatopia that electricity is really expensive, and businesses are failing, and little kids are going to sleep at night cold because they can't afford to heat their houses. So Renewatopia thought, what can we do to help deal with this high cost of electricity issue? And they decided, let's think about this from a systems perspective. So let's think about this. The wind output actually is kind of complementary with the solar output. And in addition to that, the load actually looks like this. The load isn't a flat line. So the fact that you're trying to get our wind and our solar output to be a flat line doesn't really help you when your load looks like this. So they took a systems perspective and looked at this in terms of their whole load, wind, and solar resource. And they were able to reduce how much storage they had. And they were able to bring the price of electricity down in Renewatopia. So this is nice. But still, electricity was a little bit expensive there, and they weren't able to attract, say, the industrial customers that they would have liked to their land. And so they thought, OK, what can we do to further reduce the cost of electricity? So they thought, OK, well, what if I was in Renewatopia, California, talked to the Renewatopia, Arizona, and the Renewatopia, Oregon folks, and we all sort of worked together, and we got help from our neighbors in dealing with this. And each of these circles is meant to be sort of an individual balancing area. That is, each of these circles is an area where the utility there has got to balance out their supply and demand, their load and their generation. And they thought, instead of us each doing this on our own, what if we do this all together and work in a sort of wider geographic area? And it turns out that if you look at the wind in any one of these Renewatopias, it's kind of noisy, and when you aggregate it over the larger geographic area, it actually smooths out. And not just the wind smooths out, but also the solar output smooths out, and the load even smooths out. So they were able to help mitigate some of the variability of these resources by pooling together. And this is some of what I'm going to talk about today. This might be Renewatopia in the far-off distant future. Let's look at where we are today. So today, especially in the West, in the western US, we've got a lot of these fragmented individual balancing areas where utilities are trying to balance their supply and demand on their own. We've got a little bit of wind, we've got a lot of thermal generation, some hydro generation. We've got very little solar as a percentage of our energy. But we've got a lot of these fragmented balancing areas, except in California. California is special, so you guys are all special, but the rest of the West has got issues. So in order to get from where we are today to, say, where we might be in the future, this study and what we're trying to look at is a transition time. How are you going to get there? And in this transition time, what we're looking at in this study is 2017. And we're looking at, OK, what do we need to do? How do we work with our neighbors? How do we deal with storage? How do we put the system together in a way that's going to work, be reliable, and use a lot of renewable energy? So for those of you who aren't familiar, I just put in a couple slides here on the US power system, since I know this may be a broad audience. So a real quick background on the US power system. There's 3 electrical interconnections in the US. You've got the Western Electrical Interconnection, that's called WEC, the Western Electricity Coordinating Council. I'll talk a lot about WEC. You got the Eastern Interconnection, and then you've got Texas. And Texas, I think they're their own interconnection so that someday they can secede from the rest of us, but I'm not sure. Anyway, I'm going to talk a lot about the Western Interconnection, WEC. The interesting thing about WEC is that there aren't a lot of markets. There aren't a lot of independent system operators or regional transmission organizations like the California ISO that band together a number of utilities and have them cooperate in how they run their utility operations. In the East, you've got lots of them, and some of these are really big. PJM is the same order of magnitude as all of WEC. So some of these are really huge operations. But in the West, for the most part, things operate the way they've traditionally operated. There's a bunch of small individual utilities running their own operations and balancing their own supply and demand. A real quick view of how utilities do their planning and operations, and they all do this a little bit differently, but generically speaking, if you're going to plan for, say, tomorrow at noon, the utility will be looking today at their load forecast, and they'll be looking at the weather and, is it a weekday or a weekend, and figuring out what their load's going to be for tomorrow. And they'll be thinking, OK, I think at noon I'm going to need 300 megawatts of this coal unit, and 200 megawatts of that gas unit, 100 megawatts of this hydro unit. And then the next day shows up, and it's, say, 11 o'clock tomorrow. And that's the scheduling period, the sort of day ahead. The next day shows up, it's, say, 11 o'clock, so maybe an hour ahead of the operational time frame. And the utility realizes, OK, I missed my forecast a little bit. Actually, it's hotter than I thought it was going to be, and so I'm actually going to need this gas unit to be up at 300 megawatts and this hydro unit to be up at 150 megawatts. And so they may tell the units, OK, we've got to readjust for noon. And that's this load following time period. And then you've got units, so noon shows up, and you've got units that are on regulation that are automatically controlled and pulsed by the utility every several seconds. And these pulses tell the units to go up and down depending on fluctuations in the load. And those fluctuations in the load are things like, the Walmart's chillers just turned on, or some arc furnace just turned on. And those things account for those really fast fluctuations. And that's the regulation time frame. The really fast seconds to minutes kind of wiggles in the load. So the things about wind and solar that really bug utilities are the variability and the uncertainty. So by variability, I mean that your wind and solar output are changing over time. A cloud is moving over your solar panel. It stops being windy for some reason. And these time scales, it's variable over different time scales, over the minute-to-minute time scale, over hours. There may be wind fronts moving in over the course of a day and over different seasons. In the summer, it's usually really sunny, but not very windy. And then the other thing about wind and solar that utilities have a problem with is the uncertainty. So what I mean by this is that you can't perfectly predict the weather tomorrow. So wind and solar generation, you can guess at what you think it's going to be. You can forecast it out, but there's always some forecast error. The important thing to recognize is that the power system is designed to handle the variability and the uncertainty in load. So load is already variable and uncertain. So the power system and the utility operators and all of that infrastructure already can handle some variability and uncertainty. And the wind and the solar are adding to this. So they're making their job a little bit harder. And the question is, how much are they adding to this, and when do you start to run into problems? So now I'm going to turn to the Western Wind and Solar Integration Study. And this is a study that we undertook over a period of almost 3 years, 2.5, 3 years. And this followed on to some work that DOE and NREL had done looking at the potential of the US sourcing 20% of their energy from wind. And they did this big analysis, this 20% wind vision study. They didn't find any insurmountable barriers to the to the US getting 20% of its energy from wind. And as a result of that study, DOE and NREL decided we should take this to a deeper level and look at how the system can actually operate with large amounts of wind, and in the case of the West, solar on the system. So we've actually got a companion study to this, the Eastern Wind Integration and Transmission Study, that looks at the Eastern interconnection. Here I'm focusing in on the West. And so the question we're asking is, can we integrate 35% wind and solar energy in the West? And we're specifically looking at operational impacts and economics. And here we're modeling all of WEC, all the Western interconnection, even the parts in Canada and Mexico that you can't see here. But the part that we're really going to focus in on and drill down on is WestConnect. And WestConnect is the group of utilities in this dark blue area. WestConnect is a group of utilities that's banded together to not form an ISO or an RTO, but take small steps that head in that direction. Basically, they're trying to enhance the effectiveness of their wholesale electricity markets, and they're taking steps in that direction. Now, the utilities and the public utility commissions and the developers and planners had a lot of questions they wanted us to try and answer. Things like, how do local resources compare to remote resources that you'd have to access via long-distance transmission? Do you need more backup, more reserves, more storage? How can balancing area cooperation or geographic diversity help? How does forecasting help, and is there a role for that? We looked at a number of different penetration levels of wind and solar. The one I'm going to focus on is the high renewables scenario here. Basically, we're focusing in on 30% wind, 5% solar in that WestConnect footprint, and 20% wind, 3% solar in the rest of WEC. And it's really important to try and model all of WEC here because there's interchanges between WestConnect and the rest of WEC. And when you've got a lot of renewables on the system, stuff is going back and forth, and you need to be able to capture those flows. Now, these penetration numbers are by energy, not capacity. So if they were by capacity, the numbers would be a lot higher. But basically, what we're saying is if you're in WestConnect, of all the energy you use over the course of the year, 35% of that's coming from wind and solar. The solar here that we're talking about is mostly concentrating solar power with thermal energy storage. This is similar to the plants that you've got in the deserts of California, the parabolic trough plants, except they have thermal energy storage, 6 hours of storage attached to them. And we also looked at 30% of the solar numbers here are rooftop distributed generation PV. In order to address some of these questions about the trade-offs between local and remote resources, we developed different geographic scenarios. So we started with, up in the top left, this in-area scenario where basically we had each state essentially meet its 35% target from sources within that state. So Arizona's got the biggest load here, and so Arizona's meeting 30% of that load from wind, which is this big blue bubble, and then 5% of that load from solar, which is that orange bubble. And that's our in-area scenario. That's what we started with. Then we said, okay, let's look at the opposite extreme, the other bookend of this. So the other bookend of that is moving your resources to the best resource areas. So the best wind is in Wyoming. The best solar is down here in the Southwest. So basically, We move the resources to those places and then build out long-distance transmission to bring those resources to load. And that's our mega project scenario. Then we had an in-between, halfway in between medium scenario, our local priority scenario, where we get some of our resources locally and some from the best resource areas. Okay, so what are we modeling? So we're modeling the year 2017, and we're modeling it 3 times. So what we've done is we've taken historical load and weather patterns from 2004, 2005, and 2006. And we're trying to capture the interannual variability from those different years. You know, maybe one's a high wind year, maybe one's a low sun year. We're trying to capture those kinds of variability. It's really important that the load and the wind and the sun data all be correlated. So you can imagine when it's really hot and sunny out in the middle of the summer, in the afternoon, your load may be, you may be hitting peak load, and you may be having no wind at that time. You need to capture that correlation in there. We do statistical analysis of variability on different time scales. We try to get at, you know, what is the increased variability from that wind and solar. We focus in on some of the extreme events because it's the extreme events that really kill you here. And then we do power simulations of all of WEC. So we're basically modeling every generator, we're modeling transmission, we're modeling the loads, we're modeling 87, 60 hours of the year, and looking at you know, how much fuel and emissions for the year, and looking at which generators are getting dispatched. We go down to 1-minute simulations for some of those extreme events where we're trying to figure out if you can really make the system work through those times. One of the key things here is that in order to do all this, you need really high resolution wind and solar data. And when we started this, we did not have that. We had to commission it, and this was a huge undertaking in and of itself, especially on the wind side. You know, we're trying to model 75,000 megawatts of wind in the West here, and there's obviously not that much wind installed. So in order to try and get at what that wind might look like, we basically had to run these big weather models. So we basically had 3-tier group run this big numerical weather prediction model for the western half of the United States. What they do is they make a 3-dimensional model of the West, and they look at physical flows, and they look at the terrain, and what they do is they sample this 3-dimensional model every 2 kilometers and every 10 minutes. And then for those places where we want to have wind farms, we change that wind speed into a wind power output. And in doing this, we basically made a huge wind data set. If anyone ever wants modeled wind data, you can go there and get more than you ever wanted of wind data for all of the West, and run all kinds of fun studies. But this was a huge effort. This took a year in and of itself to do. So we do this for the wind data. We do something somewhat similar, but on a much lower resolution on the solar side. And the solar modeling is a little bit behind where we are in terms of what we know and understand about the wind modeling. But we do the best we can with the tools we've got for the solar side. All right, so now that you've got your data, you got your models, how does the system operate when you've got a lot of renewables online? So this is the middle of July. This is a week in the middle of July. And the top edge of this is the load. And the operator needs to manage their generation to that load. And when you've got wind and solar online, the operator now needs to meet the net load, which is the load minus the wind minus the solar. So basically, if you subtract out from this top line the red, which is the PV, the orange, which is the concentrating solar power, and the green, which is the wind, you get this bottom edge of this graph. And that's the new net load the operator needs to meet that. And that looks really easy, right? That looks like no problem, they can do that. Now, that's July, and this is April. So you can see in the middle of April, it's way more challenging. There's really no periodicity here. goes to 0, it goes negative, which means you're trying to export renewable energy out of WestConnect to the rest of WEC. And you can see it's very challenging for an operator to try and deal with something like that. Now, this is the worst week of the 3 years that we studied, but it just gives you a sense of some of the challenges of trying to integrate this much wind and solar. So what actually gets dispatched during that time? So this, again, is that horrible week in April, the worst week of the 3 years. When you don't put any wind or solar on the system, basically, you're operating the system with your nuclear units here in black, your steam coal units here in dark blue, your combined cycle gas units in medium blue, and you got some hydro up here at the top in purple. And then there's a tiny little sliver here that's the pumped storage hydro that's operational. And that's dispatched without the wind and solar during that same week. When you add in the 30% wind and the 5% solar, in this high renewables case, for the same week, you can see that what you've done is you've basically displaced all this combined cycle gas generation. You've really cut in heavily to your coal generation. You've moved around your hydro generation. You've got your gas turbine, combustion turbines turning on at a time when they wouldn't usually turn on. And you're even starting to affect some of the nuclear units. You know, in reality, you'd probably curtail the wind rather than affect those nuclear units. But you can see you're basically affecting everything and changing what usually gets run and when it usually gets run. And this is a huge impact on the power system and on the other generators and on the system operators. So this is a big deal. Okay, so this is what it looks like when things get really bad. If you can make this work, and we're going to talk in a bit about what we need to do to make this work, what are some of the benefits? So if we can make this work, what are some of the benefits? We can save a lot of money in terms of fuel and emissions. So if we look at that high renewables case, and this is the annual operating cost. So this is really just what we're spending in WEC in terms of fuel costs and emissions costs for a year. This is not what we're spending for the actual capital costs. But in terms of that annual operating cost, we're saving about 40% over the course of the year, and that's equivalent to about $80 per megawatt hour of wind and solar generated. We're assuming a carbon tax here, so that's also part of this cost here. So there's a significant amount of savings that we could have in fuel and emissions costs if we can make this work. Of course, some of the savings is going to go back and pay for the capital costs of the wind and solar. Should I take questions now or save them to the end?
Why don't we save them till the end?
Okay, we'll save them to the end. So some of that 40% will go to pay for the capital costs of the wind and the solar plants. But there's quite a lot of fuel and emissions that would be reduced by this. In addition to fuel and emissions, we're reducing NOx, SOx, CO2 by moderate amounts at the $9.50 gas price. Basically, if gas is high, then wind and solar are going to displace gas. And when you displace gas, you're displacing something that's clean. And so when gas prices are high, you're displacing about 25% of your CO2 and less of your NOx and SOx. When gas prices are low, $3.50, then instead of displacing gas, you're going to displace coal instead. And coal is dirtier, so you're going to get better emissions reductions. So here in the low gas price sensitivity case, you're basically eliminating 45% of your CO2 emissions, 50% of your SOx emissions, 30% reduction in your NOx emissions. And just to give you a ballpark, that's like taking 35 million cars off the road. So there's a significant amount of emission reductions that you can achieve in this case. All right, so now, what do we need to do to make this work? So the first thing we think you need is balancing area cooperation. That can take an awful lot of forms. There's a whole spectrum of what that is. It doesn't have to be a full RTO or ISO, but we need to have balancing areas working together on a coordinated basis. If you look at the variability increase when you go to this high renewables case, if you look at that variability increase when you look at just, say, the tri-state area in Wyoming, so that's sort of parts of this eastern Wyoming bit, and then you move to the whole state of Wyoming, and then move to all of West Connect and move to all of WEC, that's what this graph shows. It shows that variability decreasing as you move to larger and larger footprints. So basically, that tri-state zone in Wyoming, when we move to this high renewables case, the variability increase that he sees on a 10-minute basis is a factor of 53 times higher than what he used to see. And he just can't handle that. It's just not possible. When you aggregate across all of the zones in Wyoming and go to the whole state of Wyoming, that variability increases by a factor of 6, which is a lot better, but it's still really daunting. And then when you aggregate across all of this West Connect footprint, this is a factor of 1.6. And then across all of WEC, it's actually very similar to what it was before. So the broader the region over which we can try and aggregate some of these resources and some of this load and all these generators, the better off we are. As I mentioned, today we've got these fragmented individual balancing areas acting on their own. They do interchange with each other but on an hourly basis. So there are hourly interchanges with other utilities, and a lot of these utilities are also scheduling their own generation on an hourly basis. So if you look at their operations, this red line shows their hourly schedule. So they've got their coal unit at here, and then it's moving up to a new level, and then it's moving back down, or their gas units. And basically, the actual load is shown in here by this green line, and the difference between the actual load and their hourly schedules of these plants gets filled in by those regulating units that do that really fast up and down movement to make up for the fast fluctuations in load. When you move from an hourly schedule to a faster schedule, to say a 5-minute schedule, and that's shown here in blue, if we were to move instead to a 5-minute schedule for our interchanges and our scheduling of our units, basically the green line again is the actual load, and the difference between this green line and the 5-minute schedule is much less. That's what your regulating units now have to follow, and this puts a lot less stress on the regulating units. This is also shown here in the high renewable energy case, where we looked at the stress on the fast regulation units, and we looked at it for the case where we had hourly scheduling and moving to a more continuous schedule, and find that we can reduce the stress quite significantly by trying to move to much faster scheduling than is currently done. What else do you need to make this work? You need forecasting. So this may seem like a no-brainer to many of you that of course you should forecast out the wind and the solar if you're forecasting out the load. It's actually interesting that a lot of utilities, when they start getting into wind and solar, they don't do forecasting. It's not until they get enough experience and realize how important it is that they start to do it. But what this shows is that by not forecasting, you're leaving a lot of money on the table. In the high renewables case across WEC, if you're not forecasting, you're leaving $5 billion on the table. This is the savings that you can have just by using a forecast in your operations, by using a forecast day ahead to say, okay, I need to schedule out these units a little bit differently than I would have had I not looked at the forecast. Now, what's interesting is that if those forecasts were perfect and you could perfectly know what the weather is tomorrow, you could save a little bit more. And I know it doesn't look like a whole lot. It looks like, oh, it's just $500 million or whatever. It looks really small. It seems small, and it seems like, oh, your forecast must be really good. But it's important to look not just at average forecast errors and average values, but to look at the whole distribution. So this is the forecast error distribution. And if you focus here just on the blue bars, that's the high renewables case. And what this shows is that there are some hours way out here, a finite number of hours, where you're missing your forecast by a huge amount. There are some hours where you're missing your forecast by an amount that's equivalent to half of the installed wind generation in these scenarios. So you're really blowing it big time. And if you're on that end of the spectrum and you basically under forecast, so you think, okay, it's not going to be windy tomorrow, and then it's really windy, then it's not that big of a deal because you've committed a lot of units and you can basically curtail the wind. You always have that option. You can try and back down units as much as you can, but you do have the option as a system operator to curtail. And so on that side of the fence, it's not so bad. But on this side of the fence, let's say you over forecast. You think that there's going to be a huge amount of wind and solar showing up the next day, and then that day shows up and it doesn't materialize, and you've undercommitted your other units. And so you're way out here, and you've really undercommitted and blown it, and now you have problems. And so it's these kinds of problems that we need to try and figure out what to do. When we use the standard WEC rules for holding contingency reserves, those standard rules are that you need to hold 6% of your load as contingency reserve. Half of that needs to be spinning, and half of that can be non-spinning. But when we do that, we find that we meet all the load, and there's no blackouts or brownouts in our simulations, but we have shortfalls in our contingency reserve capacity. So what do we need to do to make up for that? And contingency reserves are important because you hold contingency reserves in case a generator or a transmission line trips. And it's really important that you've got contingency reserves online for those kinds of events. So what can we do? We can increase how much reserve we hold all the time, and that's one thing we can do. We can add some kind of storage, like add in some more pumped hydro storage. That's another option. And now it turns out we only have problems. We only run into these really extreme events and problematic periods 89 hours of the year. So to pay for something for 87, 60 hours of the year, when you've only got a problem for 89 hours of the year, you're paying a lot of money. So instead of doing something you're going to have to pay for every hour of the year, we suggest there may be other options. And one of the options that we find can be more effective and less expensive is demand response. And what that means is that you have a program where you pay certain loads to turn off when you ask them to. And this is something that Texas does. They do that for their contingency reserves. And basically, it's a program. It's not a brownout or a blackout or anything like that. You're paying them for this service that they are providing to you. So demand response, we think, is one of the important things that you need. Load following reserves, we don't find that you necessarily need more load following or variability reserves. We do find that the reserve requirements, that is the amount of variability you see, is increased with lots of wind and solar, and it's approximately doubled, this amount of variability. But because you're having, when you have this wind and solar come online, you're backing down other generators. You're turning some off, but you're backing a lot of them down. And when you back a lot of these down, you actually have a lot more up margin to move than you did without the wind and solar online. And so we're actually finding that there's quite a lot of up room to move, and that we don't need to commit more reserves to cover this increased variability requirement. So we don't find that you need more storage. And I know this is really counterintuitive to a lot of folks. What we found was that, and we've only looked at storage for price arbitrage, hourly price arbitrage of the storage. We haven't looked at ancillary services. We haven't looked at it providing regulation or reliability. That's a lot harder of a study to try and get to, and we're going to try and get to that next. But it's a lot, it's sort of paving new ground there. We looked at the existing pumped hydro that's on the system, and we found that the use of it increases a little bit. We tried decreasing costs and everything to make the pumped hydro work more, and that didn't really help. Then we said, okay, well, let's just add in a new pumped hydro plant and see if it generates revenue. Now, the tricky thing about storage is that you need to know when to pump and when to generate. So you want to buy low and sell high. You need to know when low and high are. And without renewables online, you got a good sense, oh, well, you know, low is at night and high is during the middle of the day. But when you have renewables online, high is when you miss your forecast. So when you miss your forecast big time, that's when spot prices go sky high. And so you need to know when that is. Of course, if you're missing your forecast, it's hard to know ahead of time that you're going to miss your forecast. So that's really hard. What we did was we said, OK, let's just say the storage knows when low and high is. So we gave it perfect knowledge of when to pump, when to generate. And then we ran the system. And the storage earned money. It got used. We found that it earned about an order of magnitude less than we needed it to earn to pay for itself. But you know, there's still a lot of other things to look at in terms of storage. But we're not seeing yet a need for more storage. Whoops. We find that we need to better utilize the existing transmission system that's in place. Now, you're absolutely going to need some amount of transmission within each state to bring all these resources to load. The interesting thing about these three scenarios that I showed, you know, the in-state and that mega project scenario where you build out the big transmission lines, is that we did not see very much difference operationally between those scenarios. And this was very surprising to us. We thought we would see a difference. We didn't. One of the big outcomes that we find is that the existing transmission system in the West is mostly bilaterally contracted out. So a lot of times it looks like there's no space on that line when actually there's a lot of physical space for electrons to flow. It's just that it's contracted out. Now, assuming that we can really utilize that existing space that's physically available on these lines, we find that we can actually start integrating some of these scenarios while you're building out some of this other transmission. We find that we can start building out some of these cases because it takes a lot less time to build out the wind and solar plants than it does the transmission lines. But we need to better utilize that space on those lines. So in conclusion, we're finding that it's operationally feasible for WestConnect to accommodate the 30% wind and the 5% solar if you can do this laundry list of things. And this laundry list of things is not easy, and I don't want to downplay the difficulties in trying to make this happen. But we are trying to look at the low-hanging fruit here. So in terms of, say, a flexibility supply curve, what the system needs is more flexibility. And storage is definitely an option for flexibility. It'd be a great option if it weren't expensive. But there are other options for flexibility, and some of those are maybe lower cost. And we're trying to get at what are all those options. So some of the sharing of reserves, some of the flexible generation, some of the demand response, you know, what are all those different things that we can get at that might be cheaper before we go to the storage answer. And so some of the things that we find we need to do are we need to substantially increase how utilities are working with each other and how they schedule their own and interchanges with others. Increasing the use of transmission, trying to get them to commit and dispatch on a more coordinated basis, using forecasts, having more flexible other generation online. There may be additional reserves that need to be committed depending on how much of this balancing area cooperation you have. We may need to implement or expand existing demand response programs. And the last thing, I haven't really covered it so much in here, but having wind provide down reserves, basically being able to send a signal to a wind farm and have it be able to curtail or go down to a lower set point. Now, I want to emphasize that just because we did this study, it doesn't mean that tomorrow you can go ahead and install 35% wind and solar and it's all going to work. So this is just one piece of a bigger puzzle and a lot more analysis that needs to happen. There's a whole bunch of transmission planning analyses that need to happen, dynamic studies that need to happen, more local studies that need to happen. But we've taken a shot at looking at some of the integration issues on a bulk power sort of transmission level, looking at the operational feasibility, looking at the capacity value that the wind and solar can provide. So we've taken a shot at getting at some of the issues here. And then finally, I'd like to thank the whole study team. I forgot I didn't even mention GE, who basically did the heavy lifting on the analysis here. And then the three-tier folks who did the wind data set, and the SUNY folks who did the solar data set, and folks at Exeter, Northern Arizona University, and a whole bunch of folks at NREL. And DOE funded all of this work, so kudos to them for doing that. And then if you want the full report or the executive summary, there's some executive summaries floating around, but you can download everything here. So thank you.
So we'll take questions now. Okay, actually, so let's start with the back of the room there. Yeah, in the white shirt, you. Yeah.
How much cost is associated with balancing the load and generation on a 5-minute time scale versus a 1-hour time scale? And in addition to how much cost is associated with balancing it in a much larger area versus just all that extra communication needed?
Right. So that's actually a really good question. And we have not actually quantified what that cost difference is between balancing on an hourly basis versus a 5-minute basis. But that's really quite relevant because one of the things that's come out of this is that as a result of this, the two top recommendations, that balancing area cooperation, that sub-hourly scheduling, have now been taken up by WEC and are being studied as a proposal for an energy imbalance market in the West that would look at 5-minute scheduling between balancing areas. And one of the things that WEC is trying to do now is to do a cost-benefit analysis of what that would be. And so they're actually undertaking that analysis. Unfortunately, they're not even going to get to that hour versus 5-minute scheduling cost differential because almost all of the models that are out there won't run that 5-minute scheduling. They'll only run down to an hourly time frame. And then in order to run to lower time frames, you've got to have separate models that do that. But we are hoping that we can undertake that in some new studies that we're going to do where we look at that question. But it's a really good question to try and quantify that. And hopefully we get to do that next.
Okay, could you speak a little bit to what you see as the major barriers to implementation? For example, is there new software that needs to be created to actually implement these recommendations? Is cost an issue? Are there jurisdictional barriers that would prevent the utilities from cooperating and seeing into each other's systems and so forth?
Yeah, so actually, right. So technically, what we are actually saying here is sort of like the rest of the West should do more of what California is doing, or more of what PJM or the Midwest ISO is doing. We're not actually saying that there's any rocket science that needs to get done. We're saying that there's a lot of technologies and tools and stuff that's already been done elsewhere, and we need to do some of that here. It's a really, really touchy political issue, though. The whole issue of regional transmission organizations in the West is, you don't even want to say that at some of these meetings because RTO is like a 4-letter word in the West. You don't even go there because they've tried to do this in the past. This is like the 3rd time that they're sort of trying to go in that direction. And there's a lot of resistance politically to having their autonomy taken away from them. So I'd say the biggest thing is this issue of political will and whether or not we can demonstrate that you're going to save a lot of money, you're going to be able to accommodate the renewables this way, and you should try and make this happen. The one utility that really is a vocal supporter of a lot of this stuff is Xcel. And Xcel, one of the reasons why they are is because they've got a 30% RPS in Colorado that they need to meet, and they've already got 10% wind on their system, and they know the challenges of trying to do this on their own. And they know they need their neighbors and they need their neighbors' help. And so they're one of the big utilities trying to push out and say, hey, you guys, you got to help us out here, and trying to reach out in that way. So, some of that political will might come from external targets being brought from the outside.
Yeah, maybe I missed it, but so you used, you needed some demand scenario, so presumably you extrapolated from 2010 or something, and maybe it's a little bit more overall demand than in 2010, I'm guessing.
Yes.
And then you have the existing energy infrastructure with coal and natural gas mostly.
Right.
And then you're adding to that 35%.
Right.
So then you've got the other 65%.
Right.
So did you just take what exists now, or did you close down some of the coal plants? I mean, how did you handle that?
Yeah, that's a really good question.
And then the question is, did you have to put in more, backup natural gas plants, basically, for the spinning reserve, et cetera?
Yeah, that's a really good question. I didn't even talk about any of that. I mean, there's a huge amount of stuff that goes into it, and you could talk about this all day. But basically, what we did was, we project out to 2017 using, sort of load growth for different areas, and especially in the area that I'm talking about, there's more load growth than you see in a lot of the rest of the United States. And then we basically say, okay, what's the build out that WEC is projecting for 2017? So the reason why we use 2017 is because that was the WEC case that they were running at the time. WEC does transmission planning. They look every 2 years, and they do their planning, and we were building off of what they were doing. And so we're building off of, okay, WEC is anticipating this many new combined cycle units coming on, and this many, combustion turbines coming on, and things like that. So we're using that kind of information to say, okay, we think the 2017 build-out is going to look like this. Then on top of that, we added in the 35% renewables. So we've got an overbuilt system. And then we run it, and we take a look at it, and we see, what the capacity value is of the renewables. Now, the capacity value of, and I didn't even show that stuff, the capacity value of the wind is something like 10 to 15%, and for the PV, it was something like 25 to 30%. And for the CSP with storage, it was equivalent to a conventional gas plant. And then we say, okay, that's the capacity value of those plants. Then we subtract out the equivalent capacity of those additions that we just added, and then we run the system again. So we've run the system a couple times. We've run the system a bunch of times in the process, but looking at this overbuilt system and then a system where we've sort of subtracted out generation equivalent to the capacity value that we've added in. Capacity value meaning the how that wind and solar contribute to peak load.
So you could subtract, did you subtract out coal, or it doesn't matter what you subtract?
So we subtracted out the new additions. So subtracting out the coal would be, this is a whole, you're getting at a really good point, because we didn't look at different kinds of retirement scenarios. So we assumed that the coal that's there is going to be the coal that's there then. And what we could look at, and which would help a lot, and which would probably be the case if we're going to move to a high renewables future, is that you're going to be changing over some of these older units and replacing them with, newer, more flexible units. And that's going to help a lot. So this is sort of conservative because we didn't look at that. So you're right, in that case, it would look a lot better, because you'd probably be, if you're going to be planning for a renewable energy future, you're going to be planning for much more flexible generation than the kind of generation we've got and the kind of generation that is being planned.
All right, how about the right up here?
What are the time constants for some of these generators, like hydro or?
Yeah, so that's a good question. So how fast can they ramp up and ramp down? And so what we did was we genericized this. We don't model every single generator and its specific capabilities. We have sort of general classifications of generators, and then approximately how fast they ramp up and down. And of course, the gas CT units are going to ramp a lot faster and be able to start up a lot faster than the steam coal units. But basically, we use what the WEC folks use in their transmission planning. So it's the same sort of, and the coal units are pretty slow. But that's a good question. I don't have the numbers off the top of my head, but one of the things about the coal unit cycling is that one of the things that we did not incorporate into this, and one of the things that none of the integration studies have really incorporated into them, is the impact of some of that ramping. Because so if you go talk to a utility, they'll tell you, oh, my coal plants will never do that. And you show them that horrible slide where the coal is going up and down, and they'll say, our coal plants are never going to do that. And while we were using sort of standard ramping numbers aggregated from standard studies, what we don't have in here is the real cost of the wear and tear that's incurred on those units when you make them cycle off or ramp down deeply. And the reason why is because it's proprietary information. We're now in the process of trying to get some of that genericized so we can use it, but right now no one uses it. I mean, WEC doesn't use it in their studies either because it's proprietary.
All right, how about the blue shirt back there, and then we'll go down there and then come back.
So your conclusion was that more grid storage was not needed, given some assumptions, like you could rearrange the whole transmission line operating arrangement and build a whole bunch of more stuff and move things around. If you take sort of the 10-year construction reality on transmission line, does that change the conclusion on storage? And I'm curious, did the Eastern study also conclude that storage was not needed?
So yeah, the Eastern study also did not find that storage was needed. The Eastern study needs a lot more transmission than the Western study does because of where the resources are and where the people are, and that they don't have as good resources as we do here in the West. Yeah, you're right. The whole thing about the storage issue is that it depends on what of the laundry list of stuff I put up there. What are you able to do? I mean, if you can get a little bit of balancing area cooperation, but not a whole lot, if maybe you've just got like some kind of energy imbalance market and that's it, and you can't get coordinated scheduling or unit commitment of your units, and maybe, yeah, you need to have more storage. It kind of depends on how much of this kind of stuff you can get, how much of this increased utilization transmission, how much of this sub-hourly scheduling you can get, how much of the balancing area cooperation you can get. We viewed storage as sort of, because it's more expensive, we tried to look at lower hanging fruit options. And if we could make those lower hanging fruit options work, we thought, let's try and go for that instead. But if there are constraints around how much transmission you can build, and you've got transmission congestion, you don't have balancing areas working together, then you're going to need to go to storage. So it's all going to depend on what this actually looks like. We kind of made this, I started with Renewatopia, and it was sort of a joke, but sort of what we're talking about here is a little bit of a Renewatopia too, or a little bit of a utopia. I mean, having balancing areas work together, sub-hourly scheduling, using the transmission to the full extent. A lot of this stuff is we've got a ways to go before we get to there in the West.
All right, we'll go here and then come back over here.
So I didn't notice you quantifying the cost savings, and then you mentioned there might be some wear and tear and maybe spinning reserve expenses for running some of the plants that are idle. What can you quantify beyond just saying fuel costs? What the roughly dollars per megawatt hour savings would be generated in these scenarios, and would it be appropriate to say that renewables need to get their life cycle cost of energy below that before it becomes a net benefit to the grid?
So if you take those fuel and emissions savings, that 40% savings, and you divide that $20 billion by the megawatt hours of renewables that were generated, it's roughly $80 per megawatt hour. So I guess what we're saying then is that you'd need to get renewables below that $80 per megawatt hour number. But it also depends on the price of natural gas and a whole lot of assumptions that are going into this. So it always gets really dicey when you say what the target is for your cost of energy. Mr. Wind and Mr. Solar guy. It always gets really dicey because it depends on so many factors, and certainly things like what you're assuming for natural gas prices and carbon taxes all play a pretty big role in that. But $80 is the number you're looking for.
All right, right there, yeah.
Thank you. How do you get from you don't need new storage to storage is expensive, and then back to maybe you need more, and then back to storage is expensive? Wouldn't storage by paraffin synthesis have a very steep negative cost? And did you use the Department of Energy's Energy Information Administration's fossil fuel forecasts? And if so, for how many years out? And carbon is $557 billion subsidy worldwide. Do you really mean to say that we're going to go into the tax territory?
So maybe you can pick one of those.
All right, so that's a whole bunch of stuff that you want to talk about. So any study you're going to do, you're going to make, there's so many parameters and so many assumptions you've got to make. One of the reasons why we chose 2017 was so it wasn't too far out, and we wouldn't be making too many assumptions, but we still had to make some assumptions. And so we tried to do some sensitivities, like around the prices of natural gas, because that's pretty volatile. And we chose what we thought was kind of a medium number for carbon, but you know, we could run sensitivities on the carbon number as well. That carbon number amounts to about, say, 10% of that fuel and emissions cost savings that I was talking about. As to the storage question, we have to really carefully caveat everything we say because so much of this stuff, these are all moving parts. And depending on which things you're doing and how much you're doing them changes the answer. So when I talk about substantially increasing balancing area cooperation on the one extreme of that, we have a full market like we do in the Cal ISO or PJM or MISO, and we've got balancing area consolidation. On the other end of that, we just have what program we've had previously in WEC, which is the ACE diversity interchange, where they're just sharing the real fast area control error, and that's it. That's also balancing area cooperation. And depending on which of those things and all the stuff in between you choose, you will need slightly different other things here. So, you know, if you're limiting your balancing area cooperation to something that's very limited, then you might need storage or you might need to commit additional operating reserves. But if you're moving at the other extreme to something where you really have the utilities working together to jointly schedule in their units and dispatch them economically on a wide region, then maybe you don't need those things. So it's a lot of this stuff is an it depends kind of answer. And I know that may not be very satisfying, but that's sort of the world we live in, too.
We'll take just one more question in the back. Sorry, I know there's a lot of interest, but yeah, you in the green shirt, and then we gotta go. Thanks.
Sure. So the 35% scenario sounds great, but I'm thinking beyond the year 2017, right? Say we try to move somewhere around 50% in the near future after that. I'm wondering if you have any kind of sense of maybe some pathway dependencies that are involved in creating a system like this, that if we then move on to, say, a 50% system, it's going to have to look fundamentally different, and maybe storage would become a very large component, or if we don't do that now between 2010 and 2016, then we kind of put ourselves into a pickle down the road.
Mm-hmm. Yeah, so I think this is a really good point, is how you're planning for the future and what that transition time is going to look like. And first of all, I don't want to say we shouldn't be doing research on storage. I think we absolutely do need to be doing research on storage, and I think we need to be bringing the costs down, and I think that's going to play out great for us in the longer term. But right now, I also think that we don't want to use the lack of storage as an answer for why we can't do renewables, because I think we can do more renewables. But to get more at your question, so we actually have recently or are in the process of getting this report approved, an 80% renewable energy future study. And in the 80% renewable energy future study, where we're looking nationwide, we do see a big role for storage, and hopefully that report gets released sometime soon. There's one of the studies that was posted up on the website that advertises this talk is the All Irish Grid study. And in Ireland, they've been looking also at storage. They don't see storage becoming cost effective until they hit like 50 or 60% penetration of wind. But maybe I think that's something for us to start looking at where is that point where we see storage becoming cost effective, and how do we plan for that? I think the other thing that sort of relates to what you're saying is that we're going to need to plan out for this transition, and we're going to need to start thinking, because all the decisions we make today for what kinds of plants we install today have a 50-year lifetime. And so if you're not installing, flexible generation today, and you're installing some baseload coal plant that can't move, then you're kind of stuck with that for 50 years, and you've got to be able to deal with that. Maybe you're going to need more storage to deal with that and flexibility. So trying to start thinking now about how we value and quantify flexibility in the system, which we're currently not really doing, and we currently don't really have good tools and ways of doing this, is going to be really important.
Okay, well, I think we've come to the end of our time, so thank you so much.
Thanks, Sally.
For more, please visit us at stanford.edu.